All right. Let's turbocharge Kubernetes with offloaded OVN and OVS on DPUs.
Good afternoon, everyone. I'm Amit, and I'm here with my colleagues from NVIDIA and our partner from Reddit. We are excited to talk about DPU, DPF, and hardware acceleration using OVN Kubernetes CNI. I know it's a long title, almost like a sentence. We tried asking 4 different chatbots, and this is the best we could come up with. But it clearly outlines our entire agenda. So let's jump straight into it. Next slide, please. So what are we going to talk about today? To start with, what the heck is a DPU? I believe most of the folks in this room would be aware about DPU, but just in case if someone doesn't know, we'll start with some basic. Next, why did we decide to build DPF? What were the pain points of managing DPUs at scale? How was our life without DPF, and the immense value that DPF now provides? After that, my colleague Aline will walk you through service function chaining and how traffic moves from one endpoint to another endpoint on the DPU. Post that, of course, this is OVS conference, and we need to talk about how amazing OVS and OVN Kubernetes CNI is. So we'll walk you through hardware acceleration between 2 pods using OVN Kubernetes CNI, some pre-recorded demos, and some performance benchmarking numbers as well. And finally, Eagle will talk about the integration side of the story from the Red Hat, or dare I say, he's going to complain about how painful the integration was and how much hard time we gave him. Next slide. All right. So what is a DPU? DPU, or data processing unit, as shown in the picture, is a powerful beast who was designed to offload and accelerate infrastructure tasks like networking, storage, security in data centers. The main idea over here is to offload CPU cores, x86 cores, from doing infrastructure tasks so that they can focus solely on running customer workload pods, VMs, containers, etc. Specifically, Bluefield 3 DPU, the one that is shown in the picture, is a powerful beast which has 16 ARM cores, 2 physical ports, each with 200 gig, total allowing you to have a 400 gig line rate for your data and networking traffic. Next slide, please. This slide shows the fundamental shift in the servers. On the left-hand side, you have a traditional server where your CPU is spending bulk of your time in doing the infrastructure-related tasks like networking, storage, security, etc. And on the right-hand side, you have a DPU-accelerated server where all the infra-related bits are moved to the DPU and running on the ARM cores, so that your CPU can now focus on solely focus on VMs and containers, and allow you to have drastic improvement in the performance and efficiency. Slide. All right, so we have this powerful machine. We want to manage it in a data center. And these were the pain points of managing this DPU at scale. And this is how our life was without the DPF. And these are some of the main reasons we decided to build DPF. First one is provisioning. To get the DPU up and running, you need a BFB file, Bluefield boot file, which contains DPU operating system, firmwares, libraries. Along with that, you need a bf.cfg file, which is, think of it as a cloud init for DPU. And then you have command line utilities like bfb install to actually do the provisioning. Now you can do that for one DPU, but if you want to do it at scale, you would need custom scripts, Ansible, PSSH, or some Redfish, external Redfish API server if you're trying to wrap around the Redfish API. But all of this is error prone. You make one mistake here and there, and you would end up reprovisioning or reflashing the entire DPU, which is a quite time-consuming task. It takes 30+ minutes per DPU to do that. Next one is service deployment. Assume you are able to somehow get up the DPU up and running. The next task would be you would want to run some services on top of it. It could be HBN, OVN, some third-party services, or your own services. And not only you want to run them, you want to maintain the life cycle of it. So you want to upgrade them, you want to delete them, you want to steer some traffic through them. All of this will require a complex configuration and a lot of manual steps to achieve that. Third one is visibility. So assume you are able to bring up the DPU to running state and you're able to get the services also up and running. The next thing you would want to know is at any given point of time, you would want to figure out what's the health of my fleet, how many DPUs are up and running, if any service crashed, if my DPU went out of memory. All those questions you would want to answer at any given point of time. And if you have done your step 1 and step 2 manually, doing the day 2 operations would be incredibly challenging on your sandcastle. Fourth one is upgrades. Since this is again a quite challenging topic, you have so many moving pieces like BFB upgrade, services upgrade. You have compatibility checks. For example, service A can only run on BFB greater than 2.9 version. You would want to control that. You would also want to control the coordination between hosts. For example, when upgrades are going on, you don't want to accept the new workload on the host. You also want to control the speed of your rollout. You don't want to make one silly mistake, roll it out on across your cluster and bring down the entire fleet all at once. And finally, the fifth point is around specific value-added use cases. So there are some common use cases like multi-tenancy, hardware acceleration for pods. These are critical if you want to make the most out of the DPU or if you want to get the value out of the DPU. If you don't have a proper framework, let's say 1, 2, 3, 4, then you would have to do a lot of complex infrastructure code to achieve that. And it would be quite, it won't be quite right for everyone to sort of reinvent your own wheel for the flagship use cases like this for the TPF. Yeah. Next slide, please. Okay, one more slide with a lot of text. Sorry. So that is how DPF was born to address the concerns mentioned in the previous slide. Of course, DPF is much more bigger project than just what we are trying to show over here. It is quite feature rich. It solves a lot of use cases. But what we are trying to show over here is just a core set of features and like one particular use case of hardware acceleration. The point that I'm trying to make is like whatever we are showing over here in this presentation, in this 20 slides, DPF is much more than that. All right. So the previous slide focused on the why part of it. This and next couple of slides will be just what and how part of the DPF. At the core of it, we rely heavily on Kubernetes and custom resource definition and controller mechanism of the Kubernetes. First one is for the provisioning. So we have DPU sets here. You can pick the choice of your DPU flavor, which has the bf.cfg, and you can pick your BFB file, and you can target the set of worker nodes, set of Kubernetes worker nodes, saying that hey, I want this to happen on this set of nodes, and our provisioning controller will take care of rolling it out in a staged fashion for you. It will also sanitize the configuration for you, so nothing messy happens over there. Second one is service orchestration. So we provide DPU service here for that. You can containerize your application. You can write a nice fancy Helm chart for it. And there is an abstraction called DPU service where you can reference your Helm chart. You can target, I want to launch this on this set of specific nodes. And the controllers will take care of launching the actual pods for your service. Next one is service chains. So apart from just running the pods or spinning up the pods on the DPU, we will also take care of how the traffic flows through those services. And we provide a bunch of abstraction like DPU service interface, DPU service net, etc. for the user. Third one is observability. So as I mentioned in the previous slide, you would want to know once the DPUs and services are up, you would want to know, you would want to select the cluster and say like, hey, I have a lab of 100 DPUs. I want to see, let's say 60 green, 20 orange, and 20 red. On those 20 red DPUs, whatever you have defined, you would want to see what went wrong, whether the provisioning failed, whether the BFB install failed, whether like some service crashed. Some nice visualization via dashboard will help you to do your day 2 operation. On top of that, we also wanted to define a budget, saying you can define, let's say I have 100 DPUs worth of lab. If at any given point of time, 10% of the node goes down, please notify me so that I can know before our users know. Fourth one is upgrades. This is again a really cool feature. Team has spent a lot of time on this. So we have a DPU deployment CR where what you can essentially say is I want this BFB to run on this set of machines with this particular set of DPU services with this DPU service chain configuration. Basically, a single CRD, which covers or represents the entire DPU in its entirety. And it also helps us in specifying things like version compatibility check, where you can say, okay, this service goes only on the BFB version greater than some, let's say 3.0 or something like that. And if it doesn't satisfy the criteria, it won't even touch the upgrade. You also have a complete control over your upgrades. So if you have critical workloads running and you don't want to, like, let's say, go all out, you can reduce the budget. So at any given point of time, it won't touch X percentage of nodes for the upgrade, whatever you have defined in your budget. And finally, the built-in use cases. So for multi-tenancy, we have HPN, and for hardware acceleration of workload pods, we are using our beloved OVN Kubernetes. Next slide. So this is okay, good. This slide has an image. This is a typical deployment of DPF, where we have one main Kubernetes cluster where all the core DPF controllers and CRDs are running. In a host trusted mode, this manages the workloads that is running on the host as well. And for DPUs, we have small Kamaji-based clusters. So you can see DPU Kate as cluster 1 up to N. Today, we support one cluster per 1K DPUs. So let's say you have a lab of 5K DPUs. You would have one main cluster, DPF cluster, and 5 DPU K-test clusters. All of them are managing the DPUs. This is a typical host trusted DPF deployment will look like. Next slide, please. Once DPUs have joined the cluster, you would want to, let's say, launch your pods on it. The way it works is, as I had mentioned in the previous slide, the abstractions are there for you to use. You can containerize your application, create a Helm chart out of it, and specify the link of that Helm chart in the DPU service abstraction. You apply that YAML in the main cluster, and the DPF machinery kicks in. It will convert that CRD into, we use Argo CD framework, so it will convert that into Argo CD specific CRDs, and eventually it will translate into the daemon set for the DPU K-test cluster. And since you have specified that I want to run this specific service on this set of machines via node selector, once it reaches the DPU K-test cluster, it will target the set of nodes for you and spin up the pod for you. So let's say you have 100 DPUs again, you want to launch service 1 on first 50 nodes, and you want to launch service 2 and next 50 nodes, you can select the nodes accordingly. And this is the common theme for the entire DPF project. Like, you have CRDs and abstraction for everything. You specify it in main cluster, then controllers comes into the picture. They convert it into something for the Kamaji DPU clusters. And then finally, eventually, either pod comes up on the DPU or some open flow program will be programmed on the DPU. But some magic will happen on the DPU, and we will hide all of that via abstraction for you. Yeah, and to talk more about magic, I would like to talk about SFCs.
Thank you, Amit. So I will present service chaining inside DPF. I particularly do not want to include service function chaining because we're not doing transition from A to B. We're just allowing DPU services to talk in between each other. And basically, we'll have sets of services that can talk in between each other. So we don't have a transition from A to B to C and so forth. Service chaining is just an open flow controller. So in order to function, what do we need? We need a bridge. So for that abstraction, we have the CR DPU service NAT, which will create a bridge and allow us to plug a resource type. I wouldn't go over the IPAM or the service MTU, but resource type is important because it allows us to select different type of hardware resources that we can offer. So we took as an example here a scalable function. We could have a virtual function. We could also have VET. That's another use case that we support. Now, once we have a bridge, we need ports inside, right? So for this abstraction, we have the CRD DPU service interface. This will be the one that actually plugs the port inside the bridge. And here we tie that port to a service, and that service, that port will be annotated on the metadata with the service name. We have a metadata called DPF ID. It's similar to the iFace ID that OVN uses, it's just on the DPF side. And then we have the port abstraction that says who can talk to who. And this is the DPU service chain. And basically, like, we define switches, and on those switches we define ports which can talk in between each other. So this allows us to define service to service or service to uplink, uplink to service kind of scenarios on the DPU side. Now, in order to have the actual SF or VF or VET inside the workload, we need a CNI. So we also have the service chaining CNI. It's a secondary CNI that runs on the DPU. By default, it plugs the ports on the BRSFC bridge, but it can be, again, used in combination with DBU service NAT to put it into different bridges. And yes, it will also add the metadata that's specified inside the DPF service. Okay. And the service controller is just a chain abstraction and allows you to filter metadata, and basically you can say which port can talk with which port. It's pretty straightforward. Now, I would like to illustrate one of the use cases that we support. So this is DPF using just OVN Kubernetes. So because we have DPU on the host side, we will need Multius, and we also accelerate the workloads. So we'll need Multius as a SRV device plugin. So this will allow us to have a pool of VFs and Multius to plug those VFs inside the pods. And OVN Kubernetes CNI in host mode, that will be the CNI that will glue those two things together. And on the DPU side, we have OVN Kubernetes in DPU mode, which is managing BR OVN, similar to BRX that people are familiar with it. We just have a different naming here. And on the integration bridge, the representative will be plugged. And we have a patch port in between the integration bridge and BR OVN. And then we have another patch port on the BRSFC side. So basically, like, we have three open flow controllers here. We have BRSFC, which is controlled by the service chaining controller. We have BR OVN, which is controlled by the OVN Kubernetes in DPU mode. And we have OVN controller, which is managing BR end. Now, this is more complicated because we add another service. So we add HBN here. HBN is just Cumulus OS inside an image that runs on the DPU. That's it, basically. Like, it's a full-fledged router that you can either use it to do routing, BGP, firewalling, ECMP, and so on. So it has all the goodies. In our case, we use it in conjunction with OVN Kubernetes. And on the host side, we have the same things: Multius, SRV device plugin, OVN Kubernetes CNI host mode. And on the DPU side, we have the integration bridge, BR OVN, BRSFC, and BR HBN. We actually have here 4 open flow controllers because HBN is a service that listens on netlink events, and based on the netlink events, we'll add open flow flows on the HBN bridge. And everything that we have here will be accelerated because we designed the whole system to use OVS Docker underneath. So those open flow flows will just be translated into a Docker pipeline that will accelerate everything. Right, so moving forward, some performance numbers. They're really bad in the sense that they're really small as an image. But out of a theoretical maximum of 400 gigabits, we can see that on the left-hand side, we got a really nice number, 380. What I want to highlight here is not necessarily the actual bandwidth, is more on the other parts, right? Because we're running everything inside the DPU, so that means our CPU cores will be just what the actual application and the client will use. On the power consumption is similar to a SmartNIC plus 2 or 3 watts. And on the memory, again, is just the client and the server. And now I will hand it to Igal to complain about this.
Thank you. I'll try not to complain, actually. But let's see, like, we got this beast, right? And we needed to integrate it into real system, actually. not only vanilla Kubernetes. So we are starting to change the cluster network operator. And then we needed to like migrate from downstream image that guys had into upstream mode, right? Like use upstream, not downstream. We used the OpenShift type, like our solution for the hosted cluster, and not the Kamachi, like HyperShift one. We needed to move to Arcos from Ubuntu. It was interesting. And we need to adapt all the OpenShift operators, like to behave the same as the upstream counterparts. And all the security model is on OpenShift. It's like pretty different, right? Like when you are Kubernetes. So we just wanted to show like what's the difference. You can see this is like simple, right? Abstraction of how actually it looks like. It's like OpenShift regular one without DPF. So you have the worker node, have the master node, have a couple of pods connected through the like OVN Kubernetes to the OVS, right? To the BR export. Like pretty simple. Then you're starting to add stuff in order to run the DPF operator, right? You need an FD in order to label nodes with relevant hardware. You need SROV. You need HyperShift. You need MetaLB in order to make HyperShift like highly available. You need storage for the HyperShift, and it's like starting to be even more complex. Then you remove OVN Kubernetes. You remove the OVS from the host. And you're starting to bring a DPF with a special port. And DPF provisions the Bluefield card, right? And then like, you need OVS Docker for the old offloading one to make it like accelerated. And it connects like through the bridge on the host, the internet. And then it started to be like part of the HyperShift cluster as a worker node and started doing. And then at the end, like everything is connected, right? And it looks much different from what we had previously. It's fine. So the first thing we needed to do was the cluster network operator. We needed to restore, like we had already this functionality. It was not used, was not tested, it was not needed actually. So we needed to restore it in order to like cluster network operator. You don't know, maybe it's like managing OpenShift. It's managing over Kubernetes for the OpenShift, all the deployment configuration. We need to restore the DPU host mode on it, and to define like list of features that we can use in the DPU host mode. And this was like OVN Kubernetes, like as I said, like shifting from to upstream first mentality. It was very difficult, probably for the guys here sometimes, like because you need to go from the downstream image that you have a specific version to the upstream community. And the key challenge here was like lack of CI. We totally understand why it's difficult. You don't have DPUs. It's totally new, so very, very difficult to create a CI. And all the code change was like in core base was like, oh, you're always broken. You search for the new version. Like, oh, this is always a mess. The two cluster model was introduced, so it's like the idea that you have actually two clusters, right? So you have the OpenShift cluster with the worker running there, and you have the hosted cluster that both DPUs, both OVN Kubernetes actually like a part of the one cluster, but they are running on two different places. And you need to provide like kubeconfig to another cluster with token, and then you have like OVN Kubernetes is now aware of both slow and high-speed networks. It's required because when you are like provisioning the DPU, you have only the slow speed network, right? You should know about it. And then you're like, when you provision, you have the high-speed network. You want to move everything to it. So currently it's done with the host CADRs from both subnets. Currently we're like supporting a pretty small set of features, but it's because nothing was actually tested. It's pretty new. I hope for the GA version we will like increase those. And currently all the workload that is running on the host is offloaded to the DPU. Everything is offloaded. Our future plans. So we want to have OVN Kubernetes as primary C9 on the hosted cluster and DPU cluster. Currently, we have the flannel. Why we have flannel? Because currently OVN Kubernetes can't run, like, you can't have two instances running on the single host, and we need, because we are open. We already support only OVN Kubernetes. We did some small POC around it, and we managed to run like OVN Kubernetes as a primary CNI for the hosted cluster, and another OVN Kubernetes manually configured to run on the different bridges. We need to enable RDMA accelerated traffic in OpenShift in order to unlock high performance networking capability. And we will start working on enable and test like most of the features that just was not tested at all. They are not tested at all. And we are discussing like if you want to implement selective pod offloading, if you need to offload everything, if you want to offload everything. We have different opinions in this. This was like work on the Hypershift cluster. As you know, maybe not, but OpenShift is a pretty huge system, right, with lots of pods. And DPU is pretty small. And we needed to start like reducing features from it in the Hypershift. So we managed like to reduce most of the capabilities from OpenShift, like from the Hypershift cluster. We reduced like we freed around like 10 GB of memory, and it provides you like the place to actually run workload on the DPU. We need to change a little bit the mind and use Flannel as a primary CNI. All the work from Ubuntu to Arcos, like it was, as I said, pretty interesting. It's still ongoing. And all the stuff around the security context requirements, it's like we needed to create it for mostly each port of the DPF in order to run. Sorry. And we wanted to show like a little bit like the test that we ran, how it looked like, right? You have two workers, two OpenShift workers with two different like with pods, benchmark pods, one for the server, one for the client. You have OVN Kubernetes in DPU service on the DPU1 and the same on DPU2 and HBN for the BGP. You have the NVIDIA switch, Spectrum, and Lean. You see the results pretty similar to what NVIDIA guys did in their lab. And it looks pretty great, right? We have a small video to show you like hope it works. So this is like the installation of the OpenShift. We already installed the 3 masters and we are adding workers to it, improving everything, waiting for them and starting to improve, like, to apply all the relevant DPF objects, downloaded the Arcos, and then the provision started, create the cluster, DPUs are created and tributing, configuring, VFs are up, and then we will start running like benchmark, just to show you that it was live, right, and not just a result from nowhere. Okay. So this is like the server one, then the client. And you can see it's finished, and we will run one more time to the same just to see that it's consistent. Yeah, it's pretty consistent, right? It's pretty similar. Thank you. If I'm standing here, I want lots of thanks for guys from the OpenShift that are supporting it all the way, right? All the time. We're getting all we need. Thank you guys from like you are doing so much stuff and supporting us as OpenShift. Thank you very much.
Thank you.
Questions?
What did you have to do to get OVS into Arcos? Did you produce a new node image for that?
Oh, it's on. Oh, so yes, like we have totally different image created customly, right? We working on the agreement, legal agreement to provide it to customers. But yes, like we created our own image on top of the OpenShift, created new layer, right, with OVS Docker. And out of 3 drivers. Yeah, we hope like to move to the layered model, the same as in OpenShift at some point, right? And when you just create your layer and use it. But currently it's not matching the provisioning process of the DPF.
So in the end, you will have a separate OpenShift release with different components inside?
Like in the GA, as I said, we hope really to move to the layered and have like just another layer for that we will build each Z stream, right, all the time. Yes, it will be like new layer. Probably it will be new image in the OpenShift, yes. Because it's currently we just have a BFB built for very specific version with very specific drivers and yes.
Okay, thanks.
Okay, then. Thank you, everyone.